Okay, good afternoon, everyone. Thanks for coming. And this is the last talk for today's last talk. So it's my pleasure to present our work. Our work focus is on a faster proximal point method for computing exact Wasserstein distance. There are many talks about Wasserstein distance, so we will talk about how to compute the Wasserstein distance. And this is a joint work with Yujia, Ruijia, and Hongyuan from Georgia Institute of Technology, and I'm Xiangfeng Wang from East China Normal University at Shanghai, China. So Wasserstein distance is a good metric to measure the distance between distributions, and also the popular Wasserstein distance has a closely relationship with the optimal transport problem. So at the beginning, I will briefly introduce the optimal transport problem. Okay, in many cases, we need to align data from multiple sources. For example, the resource allocation, we want to assign a set of access to a set of receivers so that an optimal economic benefits can be achieved. Also, if for domain adaptation in data science, we collect multiple data sets from different domains, and we need to learn a model from a source data set, which can further be adapted to target data sets. So the main concern of optimal transport is aims to find such best alignments. So given two marginal distributions, mu and nu, the optimal transport problem aims to find an optimal joint distribution, gamma star, while also the optimal joint distribution is called the optimal transport plan. So the optimal joint distribution aims to minimize the expectation based on some given cost matrix C. So we can obtain a linear programming formulation. The optimal objective function value of this linear programming problem is referred to the Wasserstein distance between the marginal distributions. So the optimal solution, gamma star, suggests the way to transport between these two distributions with the minimum cost, while the objective function value, the Wasserstein distance, can take into account the geometry of the support and also has wide applications in generative models. So if we want to compute the Wasserstein distance, we need to efficiently solve the linear programming problem. There are two kinds of methods can solve this structured linear, not general linear programming problem, but a structured linear programming problem. One of these methods is the accurate method. We can directly solve this linear programming problem with interior point type method accurately. However, the solution may be good, but the computational complexity is an important issue. Also, by considering this linear programming problem as a linear constrained convex optimization problem, we can use some prime dual type method to solve it, like the ADMM. Also, the disadvantages are very obvious, like the tedious reformulation, also slow convergence. Represented by the Sinkhorn algorithm. Another kind of method called approximation method is popularly used to compute the optimal transport problem. These approximation methods are computationally efficient, but they cannot give an exact solution. Usually, some regularization terms are added to the original formulation and get a perturbed problem. So in details, let us discuss the Sinkhorn algorithm. We want to discuss why Sinkhorn algorithm is popularly used to compute the optimal transport problem. Usually, Sinkhorn algorithm aims to solve a regularized optimal transport problem, not the original one. We add some entropy regularization on the transport plan gamma, and get a perturbed linear programming problem. However, for this regularized formulation, we can directly use the classical Sinkhorn algorithm to solve it. Also, the Sinkhorn algorithm can be considered is equivalently with the alternative maximization algorithm for the dual problem. The Sinkhorn algorithm is proven to achieve a near the capital O n to the power of 2 complexity very efficiency. However, if epsilon denotes the penalty parameter of the entropy regularization, if epsilon is very small, the matrix G tends to underflow. Also, if epsilon is small, we need much more iterations to get the solution. So our motivation is whether we can take advantage of the Sinkhorn algorithm, but not to compute the perturbed formulation, whether we can compute the exact Wasserstein distance, we can solve the exact optimal transport problem. So before introducing our algorithm, I will briefly introduce the proximal point method. So if we want to minimize a convex function f, for the proximal point method, in each iteration, we usually solve an approximation subproblem. We usually get a new point based on an approximation function. While there is a proximal term is added, the proximal term is defined based on some distance metric. For example, the Euclidean distance or Bregman distance. The proximal point method is widely adopted for convex optimization problem and with very robust convergence behavior. So we want to combine the proximal point method and the Sinkhorn algorithm. So at the beginning, we directly apply the proximal point method to the original linear programming problem, but based on the Bregman divergence, the Bregman distance, not the Euclidean distance. Recall the definition of the Bregman divergence, and also we do some reformulation. We can transfer the subproblem iteration of proximal point method to like this. Then obviously, in each iteration, it becomes a new linear programming problem with the entropy regularization. So we can apply the Sinkhorn algorithm to solve the subproblem in each iteration of proximal point method. So this is our main idea. So our algorithm is called IPOT. It has 2 loops, the outer loop and the inner loop. For the outer loop, it is the proximal point method. But in the inner loop, we introduce the Sinkhorn algorithm to solve the inner loop subproblem. However, we only use limited inner iterations. We only use L inner iterations. And usually we choose L equal to 1. We just use 1 iteration of Sinkhorn algorithm. Okay, from the figures, the first figure shows that if we just use the Sinkhorn algorithm to solve the problem, we usually get an approximation solution, not the exact solution. However, if we use the proximal point algorithm, proximal point method, but in each iteration, we use the Sinkhorn to get the exact solution of each iteration. We can obtain the exact solution of optimal transport problem. If the inexact technique is introduced, we also can obtain the exact optimal transport solution, but with a bit more outer iterations. Also, some theoretical analysis is proved, but not trivial. We both prove the exact scheme and the inexact scheme. They both have the convergent. They both have the convergence or linear convergence and some conditions. Okay, some empirical analysis on our algorithm, the IPOT method. The first analysis is to show the linear convergence of IPOT method. And usually the IPOT can converge linearly and a very large range of hyperparameters. It's not that sensitive with the parameter beta. And also the other is about the scalability. The IPOT method has approximately the same complexity as the Sinkhorn algorithm. However, we compute the exact solution, the exact Wasserstein distance, not a perturbed one. Also more experiments to show the effect of entropy regularization, and also to show why we should compute the exact Wasserstein distance and also the efficiency of our IPOT method. One of the important applications of Wasserstein distance is to learn the generative models. However, the first line is the generative model learned by the exact Wasserstein distance solved by the IPOT method, and the second line is the generative model learned through the Sinkhorn algorithm. It's not the exact Wasserstein distance. So it's obviously that due to the smoothing caused by the regularization, the result of the Sinkhorn method tends to shrink towards the data mean, while the result of the IPOT is robust to the hyperparameters. Also, higher dimension experiments on the mixed data set also show the shrinkage problem. For the Sinkhorn, if we use the Sinkhorn algorithm, only 6 digits are covered. However, if we use the IPOT method, we can cover all the 10 digits. Another application is the Wasserstein Barycenter. This application is also to show the efficiency of our IPOT method. Give a set of distributions. The Wasserstein Barycenter is defined like this. We need to solve an averaged minimized Wasserstein distance with some linear constraints. Also, we extend our IPOT method to the Wasserstein Barycenter type, the IPOT WB. It's obviously that our method can guarantee a better Wasserstein Barycenter than other state-of-art methods. Also, at last, some takeaway messages. We proposed a proximal point method IPOT to solve the unregularized optimal transport problem, the original one. And also, the complexity of the IPOT is approximately the same as the popularly used Sinkhorn algorithm. And also use the exact Wasserstein distance in learning generative models can avoid the shrinkage problem. We propose an IPOT WB to calculate the Wasserstein Barycenter. It can generate much sharper results than the state-of-art methods. Okay, thank you.